And so really, instead of a metal, what we have is a blurred, sphere, it's a blurred surface. Okay? And then the Cooper pairing problem, which we can also do in one of the lectures, tells you that if there is a attractive interaction between two electrons, then two electrons with the opposite momentum, okay, maybe one here and one here, okay, they will form pairs, and they behave as for their interactions with other pairs, they always behave as pairs. And whenever two electrons, the two fermions behave as a pair, they become a boson. And the reason that they will form pairs is because that saves energy. So what happens is, if we were to draw an energy diagram, okay, with the Fermi energy as the reference, so above it, it will be contracted. So if we draw something like that, this is Kf, and then the Fermi energy looks something like this. What happens is that this attractive interaction allows a formation of a gap, okay? And there's a state below with negative energy here, okay? And all the electrons will condense into this state by forming Cooper pairs. And
what are your axes? Can you?
Oh, okay. So this is the k-axis, and this is the energy axis. Okay, and this condensation happens.
I think some people may not understand your Fermi sea or Fermi surface. Why don't you explain that from the Fermi direct distribution viewpoint? We'll start with the Fermi direct distribution. How does it become the Fermi surface in three dimensions?
Okay. So let's think about filling electrons inside of a metal. Suppose we have something like this, and we're using the Fermi direct statistics. So the Fermi direct statistics looks like this. Right. We have one here. This is F Fermi direct. And this is a function of the energy. And over here we call this the Fermi energy. What does this mean? Okay. The Fermi energy means at zero temperature, if I were to fill in all of the electrons inside of a metal, okay, according to Fermi direct statistics, then each of them would occupy the states one by one. And once each energy state holds two electrons because of the spin degeneracy, right? So then I would fill up the metal, the energy of the electron, up to this Fermi energy. And the Fermi energy is, roughly speaking, the energy of the next electron that you inject into the metal at zero temperature. Okay, so now if we draw this on in K space, right? In K space, because we have treated our metal as a homogeneous thing, an isotropic thing. There's Kx, Ky, and Kz. Okay, you're going to start by filling in the ground state, right, which is you have 1, 1, 1, and something like this here. Okay. And then you have one here. I'm not going to draw it. So
you like your navigation?
we can't, because that one uses the periodic boundary condition. You need a different boundary condition because you need a negative K for this one.
But you can put all those on the periodic boundary condition first before you go to
Okay.
decimal thing, and then use the equation to explain why you have a Fermi surface.
Okay. So according to that equation there, when we fill in the numbers, we just fill in these vectors, these triplets of numbers, right? So we start with 1, 1, 1, okay? And then we start with 2, 1, 1, or 1, 2, 1, etc., etc. And this goes down and down. So, and then we can roughly say that the magnitude of the K is equal to the square root of Kx squared plus Ky squared plus Kz squared. Okay. And each of this Kx, Ky, Kz, if we think about a cubic metal, okay, each of them is going to be, so Kx is maybe n times 2 pi over L, okay, and then so for Ky, maybe you have m times 2 pi over L, and then expression for the total wave number, right? Okay. So now, it's based on this expression. It's intuitive if we define this as some kind of a vector, a radius vector, right? And at large, okay, when the number density becomes large and the number of electrons becomes large, effectively they become a continuum, and you no longer see the fine structure because if you were to look at them closely, you would see these grids in the K-space, right? Each of the grid marking an integer value, an integer triplet here. Okay. But when the number of particles becomes large, this roughly smoothes out, and it becomes a sphere because there's no directional preference here. When we fill things up, we start from the low energies, and then we fill up each shell, and then we go above it, and then we fill up the next shell. So to fill up the states in the metal, it becomes something like this. Okay, it becomes a sphere. If you use that boundary condition over here, we're only using the first octet of the sphere. So first, maybe I can go a bit quicker and.
Okay.
Because this.
You want to go quicker? I'm afraid that they might not even know where the Fermi surface or Fermi sphere come from. Okay. Because you just jump into it, right? We never talked about it in the course.
Right. I thought we talked about it in chapter 8.
No,
chapter 7.
Talk about Fermi surface.
Okay.
So Fermi sees Fermi.
But maybe we
do you understand that? I don't know.
I think you
okay.
probably learned
you
this
understand.
in 340, right?
So that's
in 340, you probably learned this. Maybe they didn't draw a sphere for you, but you knew what the EF meant in 340. Okay, so anyways, let's move on. Okay. So what happens is, due to this Foley interaction, you get Cooper pairing and electrons become bosons because they behave as pairs. And we know that bosons are going to condense into a boson is like condensate. So now let's move on to the next part. The next part is the theory of a dilute boson gas at really, really low temperatures. Okay, so now we're here. So we need to go a bit faster. So let me just write down things heuristically for you. So first of all, I want to make a comment on the second quantization thing. That you have already been doing, but okay, maybe you didn't call it second quantization. So in the previous lectures, when you quantized the classical electromagnetic field, what did you do? You turned the electric field, okay, maybe this is a vector, okay, as a function of position and time. Right? So first of all, you did the Fourier transform of this, and you turned this into this Fourier component. Okay? So let's think about a finite volume, so the mode are discretized. We sum over K, and we sum over the polarizations. And then the two polarizations each given by a vector. And then is the mode, which looks like e to the I omega t minus k dot r, okay, times the square root of something here. I don't remember. Okay. But
minus I omega t. We use minus I.
Oh, we use minus I omega. Okay. E to the I k dot r minus omega t. Okay. And then there's the square root factor. And then you had a creation operator. So if we just do Fourier transforms, we turn this into some coefficient, Fourier coefficient called alpha. So second quantization just tells you, okay, leave everything else untouched. Let's turn this coefficient, expansion coefficient, into the annihilation operator. Okay. And then whenever you have done second quantization, you work with states called the Fock states. Okay? The Fock states. Okay, and the Fock states is you have something called the vacuum, in which there is no photon in any mode. Okay, and then to create photons to indicate a state, you use a collection of Now let me use this product thing of the case. Okay, and then you create a bunch of particles into the mode, and this is how you would represent the Fock state. And there should be maybe, based on the number of particles, there should be a normalization factor here, but that's not important. Okay, so that's how you would do second quantization. And let me comment on why we do this. Okay? So for the case of a dilute boson gas, we can do the same thing. Okay? So if we had some wave function for the Bose particle, okay, let me call this phi. And let's not think about the time dependence now. Let's think about everything going to the ground state and everything being in a superposition of the ground and excited states at t equals to 0, okay, or at a steady state. So we have a function psi, which is a function of position only. And we can decompose this onto, let's say that the ground state is special. Okay. I use phi for the ground state. Okay. And then the ground state has a expansion coefficient of c, okay, and then plus an expansion over the first excited states. Let's say we sum over the wave numbers, and each of the first excited state has a wave function of this, and the expansion coefficient we use b here. Okay. So now we do second quantization. We just turn these things into operators. Okay, there's an operator that creates that annihilates a particle in the ground state. These operators annihilate particles in the case state. Okay. Now what is the advantage of this? Well, we have said that in many body quantum physics, both things, two things become important. One thing is the quantum mechanics of each particle, and another thing is the collective behavior, which is modeled by quantum statistics. So now the second quantization, so now this turns into a wave function operator.
The first line too.
Okay, so maybe we can write this. Okay. Yeah. The strength of second quantization really is a natural marriage between statistics and the quantum mechanics. So you have quantum mechanics taken care of by these wave functions, while the quantum statistics is taken care of by these operators and by the rule by which they commute. Okay. So this is the reason why for many particle physics, it's natural to do second quantization. Okay. So now, does everybody get my point? I'm talking about why we need to do this second quantization, because we need to consider both quantum mechanical effect and quantum statistical effect. One of which is modeled by these wave functions, the other taken care of by the creation annihilation operator. Okay?
So the quantum statistics is expressed in the phi and everything, right?
No, the mechanics is here, the statistics is here. The statistics can be derived purely based on the commutation relations. Yeah, so I'm talking about C and C dagger, they commute with 1.
So this is the operator really.
So all of these, because we're working with bosons, all of these operators can be thought of as the creation and annihilation operator for a harmonic oscillator with the frequency given by the energy, with h bar omega given by the energy of that state. Okay. Yeah. So this is the strength of second quantization, and in second quantized form, okay, we can write down. Okay.
The question: can we switch the sequence of the?
Yeah, we can. You can write C here because they don't do anything to each other. Okay. And when we do the math in the Fock states too, okay, when you operate on the Fock states, okay, these annihilation operators are going to seek out their conjugate operators, Parisian conjugates. And really, these operators does nothing on the wave function. A wave function will seek out things like operators that operate on coordinate space. Maybe you are taking the curl of E or something. Right? Then those curl operators operate on the wave function. And I'll get to that point later. Here, okay. So now, in the second quantized form, okay, now we write down the energy of a dilute boson gas by doing an expectation value. And we assume that the boson gas has condensed, everything has condensed into the ground state. So how do we write the ground state? Okay. if we have n particles, right, then it's just, I don't even need this. If we have n particles, then the ground state for a boson gas is given by, I'm going to create n particles in the ground state from this vacuum state. So, and then there's a normalization factor. Okay, and then is C dagger taken to the nth power operating on this. What does this mean? It has a very, very good corpuscular or particle-like interpretation. So this just means I'm going to start from the vacuum state and I create, remember the dagger creates, this is the creation operator. I create n particles in the ground state. So this is my ground state, where this is a state where everything is in the ground state. Okay. So we use this to denote the boson and condensate. All right, and this approximates the boson and condensate because we're forgetting about all the excited state particles. Okay, so now we're going to take the expectation value of the Hamiltonian with respect to this ground state. But now in second quantized form, the Hamiltonian doesn't look like the original Hamiltonian when you were only working with wave functions. Okay? When you're working with wave function operators, it looks a bit different. And the difference is to account for these statistics. Okay? I'm not going to show you how we do it because this is a later chapter in the book, in our course. Okay? So now let me just tell you heuristically, I think about what are the components of this energy. We're going to have kinetic energy of each particle. And the kinetic energy of each particle, since every particle is in the ground state, for each particle it should be the same. So the total kinetic energy is going to be proportional to the number of particles, right? So we have the expectation value of the kinetic energy being proportional to the total number of particles. Okay? And then we allow in the dilute boson gas the existence of a pairwise interaction. If it's a pairwise interaction, okay, then the total interaction energy is going to be proportional to n squared. Okay? So the interaction energy, the interaction energy is going to be proportional to n squared. Okay. All right. So now we can write down this. It's going to be a functional, and we can, by doing variation of principle, we can find out what is the equation of motion that governs the ground state. So I'm just going to write down the equation of motion, and I'll explain to you in quantum mechanics terms what that means. Okay. Instead of deriving the equation for you. So this is called the Gauss and you'll see that it's no different from the Schrodinger equation, except that now we have nonlinearity. And I'll tell you why we have nonlinearity. So this is this. And now this phi of r is the phi of r we use here for the wave function of the ground state, not the wave function operation. Okay. Okay, so this is the Gauss-Kitaisky equation. It looks just like the Schrodinger equation, except that for the potential part, we have some special things. Okay? So this one comes from the chemical potential, okay? And this one is here to require the conservation of the number of particles. And now let me focus on this one. Okay. So you see that now we have a potential that's dependent on the magnitude squared of the wave function. What does this mean? Well, actually we have done what's called an in-field approximation to arrive at this. So what we do essentially is, instead of thinking about the detailed interaction of each particle with everyone else, let's say that the particle interacts with the mean field that's created by everyone else. Okay? And the field, the strength of the field, is of course dependent on the magnitude squared of the ground state wave function, because that gives you the density of the particle there. Right? So we just have, you can think about this factor as some kind of mean field potential. And because of that mean field approximation, it has this nonlinearity here. Right? So now this is a good question.
The two R's are the same.
Yeah, two R's are the same. What that means is, so if you have a pairwise potential, right, you should have, pairwise interaction should be something like R minus R prime, right? But we're not going to think about something as complicated as this. We're going to say that instead of accounting for the particle's interaction with everybody else, let's take the effect of everyone else, turn that into a mean field potential, and then, right, and then the particle is basically one particle feels the collective effect of everyone else. Okay. So people, we do this mean field theory also in electrical, when we study solids, like what's the right. Roger, can we say that the effective mass theory is a mean field theory?
In a sense, yeah, when you treat all the other particles as just
yeah, exactly. So now, this because the mean field is coming from the density of the other bosons being there, so the equation is now nonlinear. Okay, but actually for our purposes, the solution is still very simple. The solution is just a constant, except at the boundary. And so suppose we were solving for this dilute boson gas confined to some container, and it would be a constant everywhere except at the walls of the container. So maybe it looks something like this. Okay, so this would be the solution for the wave function. Okay. And now, because we have said that interaction energy is proportional to n squared, kinetic energy is proportional to n. Okay. Chemical potential is certainly proportional to n too. Okay. Oh, sorry. No, there's no. Alright, so now I can define an overall wave function because the solution tends to almost a constant. I can define an overall wave function, which I will call this big psi. Okay. And this is equal to square root of n times small phi. Okay. And now everything is the same because we said that every particle behaves the same way. Okay. The overall wave function is no different from the single particle wave function if we think about its behavior governed by this equation. Okay. But now, just instead of normalizing to 1, okay, the overall wave function normalizes to n, okay, to the total number of particles. So now this overall wave function can be conveniently associated with the density, the local density of particles. Okay. So let me write this. We can always factor a complex wave function into a phase factor and a spatial part. Right? So let me write this as this bar is equal to square root of n of r times e to the pi.
Are you going to give us a break?
Sure. Okay, let's take a 5 minute.
Maybe 3 minutes break since you're pressing the time.
Okay, so let's take a 2-minute break.
2 minutes or 3 minutes break.
Okay. So if you have any questions, maybe you can ask me now. Don't ask me about the Cooper pairing or Foley interaction. We'll talk about that later. And the details of this second quantization we'll also introduce later. So now I'm just trying to tell you the power of these things. Once you learn them, you can get some very interesting things. Well, you were asking. So it can be shown, but it's not very easily. It can be shown that a collection of both particles is the same as a harmonic oscillator.
Why the gradient is kind of
Did you learn this?
I learned about.
Are you taking 5 minutes? Yeah. Wait for them to explain. It's very long. It's very lengthy.
So it's like this part is kind of expression of the exact.
Roughly speaking. Because they don't really talk to each other other than some delta functions. You use some delta functions coming from these commutation relations. And why are there delta functions? So because we can say bk k prime dagger, they commute with chronic and delta functions. And you can also say that two-wave functions, they commute. With direct you have seen these? So they only commute really through delta function. And the delta function helps you conserve stuff. Okay. This helps you conserve momentum. This helps you conserve momentum. So because they do have some crosstalk of these delta functions, it's not exactly true when I say this completely takes care of the statistical effect. This completely takes care of the they do crosstalk. But roughly speaking, all right, so maybe we can get started. So I was saying, based on that interpretation of this overall wave function, we can conveniently separate it into something like this. And the radial part gives you the number density of the particles at this point. And this gives you the phase of the compensated wave. Okay, so why do we bother separating them into this polar form? This is called the polar form for a complex number. Okay? And the reason is now it's much easier to make connections with the probability current. Okay, so if you recall, what is the probability current? H bar 2mi, okay. You have the psi, there's the conjugate here. Okay, so if I plug in the wave function here, okay, what I'm going to get is, first of all, you have 2I here. You have this being the complex conjugate of this. So right, we just write this is the h bar over m times the imaginary part of psi conjugate gradient psi. Okay. Now let's plug it in. Okay. So the gradient of this function is equal to, first of all, you take derivative with respect to this, you get 1/2. Right. Square root of 1 over square root of n of r, okay, times the gradient of n of r. Okay, and then it's I by. And there's another term which is I times gradient of psi of r times the original function. Right. So this is of course this is the real thing. And also we are going to make some approximations here. Okay. We're going to say that, well, because we have found that the number density is roughly the same everywhere. The gradient,
the Q.
Where, sorry, that's a phi. Phi, yeah. And I'm using this phi to distinguish between the ground state wave function that I used before.
J, the one line before the end.
H bar 2m.
We got that.
You know that?
Yeah.
Oh, this is the imaginary part.
Oh,
Sorry,
so
that's I. Okay, maybe I should.
No, I looks like Q.
Sorry.
Yeah, that is Q.
I'm trying to write them curly. I'm not very good at it. Alright, so now we're going to approximate this to 0, because by virtue of the solution of the Gauss-Minkowski equation. Now, what this allows us to do is now we can relate the probability current to this phase vector and the gradient of this phase vector. So we have the probability current is approximately equal to h bar over m, and this would be gradient of and then psi of r sees psi of r conjugate, which cancels the phase vector. So this just gives you n of r. Right here. Okay. So the flow of the particle is due to what the phase difference. Yeah. And it tells you what the phase is. Okay. And actually, when you solve the equation, you find that, well, the phase is pretty much the same everywhere, except at the boundary as well. Okay. And that tells you that actually all the flow is going to be localized to the boundary layer. Okay. And that happens for superconductors too. Superconductor, we have a superconductor, all the current flows at the boundary of the superconductor. There are many ways to understand this. This is one way. You could also say that because in the superconductor it doesn't like the magnetic field, okay, it will try to push the current to the boundary so that the magnetic field it creates is outside of the superconductor. You could also say that. But this is one way to look at it. So now let's couple the electromagnetic field into this. And so how do we do that? Okay. We just replace this, okay, this factor with by adding in the vector potential here. And you will be asked to do this, show this in the
You can put that in
yeah. Okay. So now, after coupling to the electromagnetic field, what we get is this is h bar over m, okay, gradient of psi of r minus q So now you see something interesting. Okay. When I couple in the electromagnetic field, you see that the current responds directly to, forget about this for now, the current responds directly to the vector potential. Right. So now if this current was something I can see, I can measure, then the vector potential is a physical quantity. And this has some consequences. So in quantum mechanics, the vector potential actually has physical meaning. And this is why. So now we derive this equation, and what else can I do? So let's see. This is okay. So now this is the probability current so far. This is still the probability current. Let me turn this into a, if I was talking about the Bose particles being Cooper pairs, which are charged, I can now turn this probability current into an interpretation of real current. Okay? And that is the supercurrent in the superconductor. So by turning into that, we just need to give it some units. So
just before you go, How do we add the vector potential on that?
Right, so you replace P, okay, with P minus E over pi. So you do something like that.
Yeah.
You throw this in the take home exam. Right. So I was saying, okay, now let's turn this current and give it charge. Okay. To do that, what we need to do is I take the n and all these p now denote pairs. Okay. So you to understand that these are referring to electrons acting as pairs. So this is not the electron mass, but the pair mass. This is the number density for the Cooper pairs, not the number density for electrons. And the pair charge. So what have I done here? Okay? So by multiplying this by the pair charge, okay, I can turn this probability current into an actual charge current. And we call that the supercurrent for the superconductor. So I multiply by EP, now I divide by it. I take this to this side and I approximate it as a constant. I take m over here. This is equal to gradient of minus there should have been part here. Q. And the Q now is the pair charge. So A. Okay? So now I arrive at an equation which is EP A plus. Okay. I'm going to call some factor of lambda squared JS. This is equal to